If you want to create a 3D hologram of a human today, you typically need a room covered in synchronized cameras. Try doing it from a single, uncalibrated smartphone video using a diffusion model, and you will either instantly run your GPU out of memory, or the AI will generate a person whose jacket blows left in the front and right in the back. Today on AI Paperslop, we are looking at a paper that solves this. It's called 4DAnyone. Create anyone in 4D from a casual monocular video. And it's by Yudong Zhen and a team from Zhejiang University, Robiant, and Ant Group.
Right.
And they basically conquer this bounded attention context problem using three main pillars. So first, 3D-aware skeleton conditioning, so using depth-buffered skeletons instead of notoriously unreliable dense metric depth. Second, reference context packing, or RCP, which compresses generated reference views into a fixed length O of one context using multiscale patchify layers. And third, target context routing, where they dynamically rotate target view groupings at high noise steps to share global structure.
Okay, let's unpack this. Because the DIT memory bottleneck is massive here. It's the whole problem, really. I mean, we are dealing with generating 16 or more target views simultaneously just to optimize 4D Gaussian splatting. And in a diffusion transformer architecture, sequence length dictates absolutely everything.
Right, because of the attention mechanism.
Exactly. The self-attention scales quadratically with sequence length. So if you try to, run 16 high-resolution video clips through the base 1 2.2 model at once, your VRAM usage just completely explodes.
Which forces you to split those 16 target views into smaller subgroups. Right, like, say, 4 views per batch, just to survive the forward pass.
Yeah, you have to.
I think of this like trying to paint a 360-degree 3D statue using a team of 16 painters. But to fit them in the room, or, in our case, the GPU memory limit, you have to put them in separate isolated booths. So the front painters have absolutely no line of sight to the back painters.
That's a great analogy. And that isolation creates two distinct points of failure. First, on the reference side, you want every new view you generate to be mathematically conditioned on all of the previously generated views.
Makes sense.
But if you just naively append every new view into the key value cache, you hit an O of n scaling wall. You run out of memory almost instantly. And then on the target side, those disjoint groups of 4 are denoising completely independently.
So they can't talk to each other.
Right. They cannot exchange structural information during the reverse diffusion process. Group A might generate an arm slightly raised, while Group B generates it lowered, and your cross-view consistency is permanently destroyed.
I see why the DIT context window is a choke point. But my immediate thought here is, why are we even using a raw video diffusion model for this pipeline? Because, we already have explicit depth models like Trajectory Crafter or implicit camera control models like Recam Master. Those architectures are literally built from the ground up for novel view synthesis.
What's fascinating here is this core design principle of accuracy over density.
Okay.
So Trajectory Crafter, like you mentioned, relies on dense metric depth. It estimates a depth map for the source frame and physically warps those pixels to the new target viewpoint.
Right.
But the issue is that dense metric depth estimation for unconstrained in the wild video is incredibly noisy. You get all these edge artifacts and scale inconsistencies.
Always it's just guessing from a flat video.
Exactly. And when you warp those flawed depth maps to extreme viewpoints, like a full 180-degree turn to see the subject's back, the errors compound exponentially. The multi-view generation just diverges into these floating artifacts.
But Recamaster approaches the problem completely differently, though, right? Using implicit controls, like Plick arrays, which is really just a mathematical way of representing 3D lines for implicit camera arrays, or spatiotemporal camera embeddings.
Yeah, and those implicit models generate videos that look visually plausible to a casual human observer. But they lack hard, pixel-perfect geometric constraints. The camera control drifts subtly over time, and that slight drift is fatal if your end goal is 4D Gaussian splatting.
Because 4DGS needs absolute precision.
It requires millimeter-perfect multi-view consistency to optimize the millions of 3D Gaussians. If the cameras drift even a little, the Gaussians cannot converge and they just turn into a blurry cloud. So 4DAnyone pivots away from both dense depth and implicit camera arrays. They opt for a highly reliable, albeit sparse, geometric signal.
3D body skeletons.
So skeletons, yeah.
But using skeletons brings up an immediate geometric ambiguity. If you just render a standard stick figure pose on a flat 2D plane, the diffusion transformer has no concept of depth. Like if a hand key point overlaps a chest key point in the image, the 2D rendering flattens them together.
Right.
The DIT cannot natively know if the hand is reaching forward toward the camera or, scratching the person's back.
Right. And to resolve that ambiguity, they use a specific 40 key point subset of the much larger 308 key point Goliath vocabulary.
Oh, Goliath. Okay.
Yeah, they extract 17 body key points, 6-foot key points, and 10 palm-level hand key points. And notice they deliberately ignore the individual fingers.
Right, just the palm.
Which becomes really critical when we look at their in-the-wild training data later. But addressing the depth ambiguity, they do not just draw 2D lines. They rasterize the 3D skeleton using a pixel-wise Z-buffer.
Here's where it gets really interesting, meaning they take the camera space depth of each physical key point and use it to drive the Z-buffer during the actual rendering step.
Wow.
So nearer body parts actively occlude farther ones at the pixel level.
Yes. The resulting depth-buffered RGB skeleton sequence gives the base model, the WAN 2.25B base model, an occlusion-aware geometric guide. The DIT can explicitly see that the arm is in front of the torso because the arm's colored cylinder is physically drawn over the torso cylinder in the conditioning image.
Oh, wow. So it completely removes the need for the model to guess the pose depth from a flat image.
Entirely.
And the mechanical implementation here is particularly elegant because they do not have to rip apart the WAN 2.2 architecture to feed this skeleton in. They pass the RGB skeleton sequence into a 10-layer 3D convolution encoder, downsample it to exactly match the DIT's latent space resolution, and just add it as a residual connection to the noisy target latents.
And we really should emphasize why they use a residual connection with a zero initialized final projection layer.
Yeah.
If that final layer was randomly initialized, the moment you inject this massive structural condition into the network, it would cause catastrophic forgetting.
Because it would shock the system.
Exactly. The model would instantly lose all the rich video priors it learned during its original pre-training.
Right, because a massive random noise signal would overpower the pre-trained weights, forcing the model to unlearn everything just to accommodate the new skeleton inputs.
Yeah. By zero initializing that final projection, the residual starts at exactly 0. So at step 0 of fine-tuning, the model behaves exactly like standard WAN 2.2.
It doesn't even know the skeleton is there yet.
Right. And as training progresses, those weights slowly wake up, allowing the model to gently integrate the rigid skeleton constraints without destroying its baseline temporal coherence and physics priors.
Okay, so the Z-buffer ensures the model won't render a hand inside a chest cavity. But geometry is only half the problem. A skeleton doesn't tell the model that the person is wearing a plaid shirt with a logo on the back.
No, it doesn't.
If you want to generate 16 views of that shirt, we have to feed the generated views back into the model as appearance reference. And as we established earlier, appending those into the DIT hits that massive O of N memory wall.
And this is where they introduce reference context packing, or RCP, to bypass that wall. In a standard DIT, if you keep adding full-resolution generated frames to the key value cache, the token count explodes. Instead, 4DAnyone alters the scaling laws of multiview generation by using multi-scale patchify layers.
So standard WAN 2.2 uses a 3D convolution for patchifying with a kernel and stride of 122, that is a temporal stride of 1, and a spatial stride of 2 by 2. I was conceptualizing how RCP modifies this, and it feels like building a multi-resolution ZIP file, or like a mosaic.
A mosaic is a good way to look at it.
RCP introduces 2 extra patchify layers, one with a 144 kernel and one with a 188 kernel.
If we connect this to the bigger picture, the 188 kernel gives you the broad strokes of the mosaic. It captures the global layout, the overarching lighting, and the primary colors of the clothing. Because of the aggressive spatial stride, it produces only 1/16 the number of tokens compared to the base resolution.
Which saves a ton of space.
Huge amounts of space. And then the 144 kernel acts as a middle ground, producing 1/4 of the tokens to capture tighter details.
And the math behind initializing these new patchify layers is clever. They do not train these heavy compression layers from scratch. They take the pre-trained 122 kernel, tile it spatially to match the new 4x4, 8x8 footprints, and then divide the weights by the area ratio, so dividing by 4 is 16.
Yep.
That mathematical division perfectly preserves the activation variance, meaning the latent representations do not blow up in magnitude before they even hit the transformer blocks.
That mosaic analogy holds up perfectly here. By allocating a strict, fixed budget of token slots for these compressed references, the complexity drops from O of N to O of 1.
So it never grows.
Right. You generate your first 4 views, you compress them with the 4x kernel, you generate 4 more, compress those, pack them into the fixed context window, and your total token count has not grown by a single token.
Oh, wow.
The DIT learns to pull high-frequency details from the source video, and it uses this O of 1 mixed-resolution context to guarantee that, the logo on the back of the jacket stays in the exact same spot across all 16 viewpoints.
So appearance is packed into an O of 1 context. But we still have the generation side problem.
What do you know?
We are generating 16 target views in batches of 4. If those 4 view groups are totally isolated from each other during the denoising process, they're going to hallucinate completely different base structures.
Yeah.
Like, the front 4 views might decide the jacket is unbuttoned, while the back 4 decided is buttoned. They have to force the groups to communicate somehow at the high noise stage to prevent that divergence.
Yeah, and they rely heavily on the temporal dynamics of diffusion models to pull that off. In the reverse diffusion process, high noise levels dictate the low-frequency global structure. Low noise levels are responsible for refining the high-frequency fine details.
Okay.
If the target groups are isolated during high noise, their global structures diverge permanently. I mean, no amount of RCP appearance guidance can fix a fundamentally misaligned torso.
This is where target context routing, which is detailed as algorithm 1 in the paper, comes in. During the high noise phase, instead of keeping the 4 view batches static, the model dynamically shifts and repartitions the ordered view indices at every single denoising step.
Exactly.
So at step T, views 1 through 4 form a group. At step T-1, views 2 through 5 form a group. Step 2-2, views 3 through 6. The groups are constantly rotating.
You are forcing the global structural context to propagate cyclically around the entire 360-degree array of target views. Because the views in a given batch overlap with the previous step's batch, the structural decisions made in one step bleed into the next.
It's like a daisy chain.
It is. They are tricking the DIT into behaving as if it is processing all 16 views simultaneously, while strictly maintaining the GP memory budget of a 4-view forward pass.
But they do not keep that rotation going forever, though. Once the global structure is locked in, they transition to a low noise phase where the routing stops. The groups become fixed, meaning adjacent views stay together.
Yeah, because constant rotation at low noise levels would destabilize the generation of fine details.
Oh, that makes sense.
Once the model is trying to generate, say, the specular highlights on a leather jacket or the micro wrinkles in a shirt, you need neighboring views to consistently cross-attend to each other. That continuous local attention ensures smooth, flicker-free transitions between adjacent viewpoints.
And the paper designates a specific switching time step for this transition as teats over t, and found the optimal value is 0.2. So out of 20 total denoising steps, the first 16 steps use the dynamics rotating groups to lock in the 360-degree structure, and the final 4 steps lock into fixed groups to polish the fine details.
This entire architecture, the Z-buffered residuals, the multi-scale RCP, the dynamic TCR, it's a highly specialized engine.
Wow.
But it is totally useless if you do not feed it the right data to teach it how to decouple a person's pose from their appearance and how to survive messy in the wild backgrounds.
The training data is always the secret sauce.
Always. The training curriculum does heavy lifting here. It is a 3-stage pipeline designed to progressively build the model's capabilities without overwhelming it.
Right.
Stage 1 is trained exclusively on DNA rendering data. This is high-quality, multi-view capture data, but they mask out all the backgrounds. It is foreground only. The sole objective of Stage 1 is to teach the model how to obey the skeleton-conditioned camera control.
And the researchers pull a brilliant regularization trick in Stage 1 to force the model to decouple pose from appearance. They implement a 20% probability of sampling the source view clip and the target view clip from entirely different temporal windows within the same video.
It's so smart,
Yeah.
because if you feed the model a source video of a person standing completely still, but the target skeleton you provide is from 5 seconds later when they're in the middle of a cartwheel, the model experiences a massive penalty if it tries to copy the static pose from the source video.
Right, it gets punished.
Violently forced to learn that appearance features, like shirt color and facial identity, come from the source clip, but geometry and spatial positioning must be strictly dictated by the Z-buffered skeleton. It completely severs that lazy temporal correlation between pose and appearance.
Then Stage 2 takes that foundation and introduces unmasked multi-view data. So they use the SynCam video dataset alongside a massive custom dataset they built in-house called MVGameHuman. MVGameHuman contains 38,000 videos captured with 24 virtual cameras inside a game engine. And this pivot to unmasked game engine data solves a specific hallucination problem, right?
Oh, absolutely. A stage 1 model, trained only on masked foregrounds, will hallucinate bizarre, noisy artifacts around the edges of a human when placed in a real scene. It has no concept of how a physical body interacts with a 3D environment.
Like lighting and shadows.
Exactly. Stage 2 forces the model to calculate proper scene lighting, cast realistic shadows onto the floor, and figure out how to stabilize complex background textures across 16 different generated camera angles. The virtual game engine data provides mathematically perfect camera extrinsics and lighting ground truth to deeply train those multi-view priors.
That leaves stage 3, which introduces monocular in the wild datasets like Pexels and TED Talk.
Yeah.
This is purely for general real-world robustness. But earlier, we noted that they deliberately dropped the finger key points from the 40 key point Goliath skeleton.
Yes.
Stage 3 is where that decision becomes critical. Monocular finger tracking from a single, uncalibrated YouTube video is incredibly noisy. If they force the model to condition on those jittery, hallucinated 3D finger key points, the generated hands would just turn into a glitching mess.
Right, so by dropping the fingers entirely, the model can no longer rely on the skeleton for hand geometry. It has to look at the visual reference provided by the source video and organically infer the hand poses through its own diffusion prior.
Which it's already good at.
Exactly. It is a perfect example of knowing when explicit geometric control becomes a liability. Sometimes, trusting the base model's prior is safer than forcing it to follow bad geometric data.
So theory, math, and training curricula are fascinating, so what does this all mean when tested? How does 4DAnyone actually perform against the current state-of-the-art when tested on unseen DNA-Rendering and DyMVHumans test sets?
Well, the quantitative metrics reflect a complete destruction of the baselines. I mean, they evaluated performance across 3 dimensions: 4DGS reconstruction quality, generated video consistency, and generated video reconstruction against the ground truth.
Okay.
Across PSNR, SMM, and LPIPS, 4DAnyone significantly outperformed MVPerformer, Trajectory Crafter, and Recam Master.
And looking at the qualitative video outputs, the reasons are pretty obvious. Like, MVPerformer can generate a very clean frontal view, but the moment the generated camera pans to the side or the back, the subject's body shape distorts and flattens out, because it was natively trained on a data set with limited view diversity, so it just lacks a true 360-degree prior.
Yeah, and then Trajectory Crafter suffers from catastrophic front-to-back failures for the exact reason we discussed earlier, the dense depth reliance. Any slight error in the initial depth estimation from the source video just multiplies as the viewpoint changes.
You see limbs just shearing off into the background.
Yeah, or the model completely failing to hallucinate the back of a subject's head. It's really rough.
The researchers even did a very fair ablation where they took Recam Master and fine-tuned it using the exact same RCP and TCR architecture. But even with the O of 1 context packing and the dynamic routing, it still failed to produce clean 4D Gaussian splatting renderings.
Implicit control just isn't enough.
The implicit camera control just does not offer the hard pixel-perfect constraints that 4DGS requires. The generated cameras drift by a few millimeters, and when you run FreeTime-GS, which is the standard 4D Gaussian optimization tool, over those frames, the splats cannot converge. They just turn into a fuzzy cloud of noise.
Because generating a single video that looks plausible to the human eye is one task. But generating 16 simultaneous videos that are geometrically consistent enough to optimize millions of 3D Gaussians through them without turning into a blurry mess, that is an exponentially harder, highly constrained task.
But we do need to address the limitations here. The paper is extremely transparent about where this architecture breaks down. And the primary failure mode is loose garments. Flowing dresses, long coats, capes, really anything that moves independently of the human skeletal structure.
This raises an important question because the skeleton offers absolutely zero geometric guidance for cloth moving far from the physical body.
It doesn't track a cape.
No, it doesn't. The multi-scale Patchify and RCP helps maintain the color and texture of a flowing dress, sure, but the structural placement of that fabric is not anchored by a Z-buffered key point.
Right.
So the model might generate a dress billowing slightly to the left in view 3 and slightly to the right in view 4. When FreeTime-GS tries to optimize 4D Gaussians across those conflicting views, you get degraded, fuzzy geometry in the clothing regions.
And that highlights a massive upstream dependency issue. Because 4DAnyone relies so heavily on 3D skeletons for its hard constraints, it is completely at the mercy of the human mesh recovery model, the HMR, used to extract that skeleton in the first place. So if you feed it a casual video of a ballet dancer and the HMR hallucinates the pose, estimating, flat feet on the ground instead of an on-point stance.
Every single generated target view will inherently inherit that exact structural error. The diffusion model will beautifully, consistently render flat feet across all 16 viewpoints, completely overriding the visual reality of the source video.
Wow.
It is the fundamental trade-off of using explicit conditioning. You gain rock-solid cross-view consistency, but you blindly trust your geometric anchor. If the anchor is wrong, your output is flawlessly, consistently wrong.
We have managed to solve 4D human reconstruction from a single casual video using sparse geometry, O of 1 multi-scale context packing, and dynamic structural routing. But if we pull back, what happens when we scale these specific architectural tricks beyond just human avatars?
That is exactly the thought I want to leave technical practitioners with today. 4DAnyone proves that O of 1 multi-scale packing and dynamic high-noise routing can perfectly synchronize 16-plus completely fabricated viewpoints of a highly complex object without blowing up VRAM.
Right.
If we take this exact same architecture, the RCP and the TCR, and apply it to full semantic scene graphs rather than just human skeletons, the implications are massive. How far are we really from feeding a single uncalibrated panning shot of a busy street from a smartphone into a diffusion transformer and instantly converting it into a fully explorable, temporally consistent 4D VR environment?
It's wild to think about.
The mathematical bottlenecks have been solved. It is just a matter of scaling the geometric anchors.
This has been AI Paper Slop. Thank you for listening.